you, sirs. Take up one idea and make it your life. Think of it, dream of it, and live for it. Let every part of your body be filled with this idea. Leave every other idea aside. This is the way to success. A man who pursues perfection in every action, who goes an extra mile for the future of young minds, who is disciplined yet gentle at heart. It is none other than our dynamic principal, Vinayaka Mission's Kirupananda Variyar Arts and Science College, Dr. V. Anbalagan, sir. I now invite sir to deliver the welcome address.
Respected dignitaries, on and off the dais, very good morning to all. With the heavenly blessings of our Honorable Founder Chancellor, Dr. A. Sanmagasundaram, it's my pleasure and privilege to welcome you all for this SCRB sponsored 4th Indo-South Korea-Thailand International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications, shortly called as iNEEBA-2024. It is an iconic event of our VMKV Arts and Science College. This event is jointly organized by Vinayaka Mission's Kirupananda Arts and Science College with Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea, and Faculty of Engineering, Chulalongkorn University, Thailand. The sole purpose of this conference is now being organized at the 4th time is to empower and advance scientific and research in the field of nanoscience and nanotechnology, particularly as they relate with energy, environment and biomedical applications. We have conducted 3 similar conferences in the past years, 2 years in online mode, 1 year in physical mode, that is 2023. Each previous iNEEBA series has established a solid foundation and is truly inspiring to witness our growth, with particularly from diverse background and areas of expertise coming together to share their insights for research and findings. I am especially proud to state that all 3 previous iNEEBAs we have published a special issue with internationally reputed journals like Applied Biochemistry, Biotechnology, Materials Today Proceedings, and Journal of Physics Conference Series. At this time, iNEEBA 2024, I am happy to state that we are going to publish the good papers submitted for this event will be published in Journal of Applied Physics A, which is Springer publisher, and Research Journal of Biotechnology, which is also Scopus Index Journal. So I hope it will continue for future years also with the support of Gyeongsang National University and Chulalongkorn University. For this great occasion, I wholeheartedly welcome our Honorable Vice President, Mr. N.B. Chandrasekhar sir, for this inaugural function of iNEEBA 2024. I welcome you, sir. He has been a constant source of inspiration and motivation for all the events organized by our VMKV Arts and Science College. I take this opportunity to welcome our Director of Vinayaka Mission's Research Foundation, Deemed University, Mr. N.V. Ramasamy sir, for this inaugural function, iNEEBA 2024. I welcome you, sir. I would like to extend warm welcome to the today's chief guest, Dr. R. Vijay, Director of International Advanced Research Center for Powder Metallurgy and New Materials, shortly called as ARCA. It is an autonomous institution, Autonomous Research and Development Center of Department of Science and Technology, Government of India. I am happy to inform you that our VMKV Arts and Science College and ARCA has submitted a joint research proposal to the DSC to the tune of 1.2 crore under new and emerging energy storage technologies. I wholeheartedly welcome you, sir. In spite of his very busy schedule, he has accepted our invitation and gracing this occasion. I would like to take this opportunity to heartily welcome our Honorable Vice Chancellor of Vinayaka Mission's Research Foundation, Deemed University, Professor Dr. P.K. Sudhir, who is going to preside over the function. Your presence today adds immense significance to the event. I wholeheartedly welcome you, sir. I also welcome our respected Registrar of Vinayaka Mission's Research Foundation, Deemed University. As we inaugurate this prestigious conference, we are truly honored with you today, sir. I extend my warm welcome to Professor Myang Myang Chai, Director, Core Facility Center for Photochemistry and Nanomaterials at Research Institute for Green Energy Convergence Technology, Gyeongsang National University, South Korea. We have entered MOU during iNEEBA-2024 with Core Facility Center and the Department of Chemistry. Professor Chai is instrumental in bringing this MOU and keeping this MOU very active and very functional. We are continuously collaborating research and faculty exchange program with Gyeongsang National University. Recently, I have been invited as visiting professor for his world-class state-of-art research laboratory. Thank you, Professor, for the opportunity. We would like to continue with the same spirit with this Core Facility Center. It is indeed great pleasure to welcome all the eminent speakers who are going to spend their precious time with us on this auspicious occasion. Professor Dr. Suradip, Associate Professor, Faculty of Engineering, Chulalongkorn University, Thailand. Tomorrow he will be joining through online. Professor Dr. S. Anandan, National Institute of Technology, Trichy, and Professor Dr. Aruna Kumari, Department of Chemistry, Oxford College of Science, Bengaluru, and Professor Dr. Sakti Pandi, Department of Physics, SRM Technical Institute, Trichy campus, and Professor Dr. Sankarlal Gar, former Principal, Holkar Science College, Indo, and he is also editor of the Research Journal of Biotechnology, and Mr. M. Sendil Pandian, Research Scientist, Department of Physics, SSN Research Center, SSN Autonomous Institute, Chennai, and Professor Dr. G. Murugadas, Scientist from Satyabama Institute of Science and Technology, Chennai, and Dr. S. Anandan is also from ARCA. Actually, he has to join today, some other unable to attend this function. Professor Dr. S. Anandan, Scientist of ARCA, and Professor Dr. Rajamalli, Materials Research Center, Indian Institute of Science, Bengaluru, and Gopalakrishnan, Researcher, Advanced Material Research, Energy Storage Conversion Laboratory, Chulalongkorn University, Thailand. I extend my warm welcome to Professor Dr. Tirthagiri, Senior Scientist, Brainfood Fellow, Core Facility Center, and he is a connecting bridge between our VMRF and GNU. Also extend warm welcome to all our directors, principals, vice principals, deputy dean, and my dear faculty members. I wholeheartedly welcome for this inaugural function of iNEEBA-2024. I also extend my welcome to Dr. Sasikumar, Principal of BMTVC. He has given all the support for conducting this conference at this venue. I also welcome my team members, organizing committee members, Dr. Jayagandan and Dr. Prakash, Dr. R. Ganeshamurthy, Dr. Saini Joy, Dr. Yogapriya, Mr. Ramesh, Mrs. Kasturi, and Mrs. Suguna, all our faculty members of VMKV Arts and Science College. I also welcome chairpersons for the technical sessions, juries for oral and poster presentation sessions, and finally organizing an event with international reputation by small institutions like our VMKV Arts and Science College is a very big task. It has become possible only because of your enthusiastic participation. I am happy to share that most of the participants, around 50 to 60% of participants, are attending this conference either third time or fourth time. It's our great pleasure and privilege. I wholeheartedly welcome all the participants from various institutions across the country and the world. Without them, the function will be incomplete. Once again, I welcome you all present here. Thank you very much.
Thank you, sir. Gratitude unlocks the fullness of life. It turns the denial into acceptance. Gratitude makes sense of the past, brings peace for today, and creates a vision for tomorrow. Now it's time for honor today's guest. I request Mr. V. Chandru sir to honor Dr. R. Vijay sir.
build products. Great leaders build cultures. Good leaders deliver results. Great leaders develop people. Good leaders have vision. Great leaders have values. Good leaders are role models at work. Great leaders are role models in life. He is a man of simplicity, elegance, and a man of letters. I now request the Vice President, Vinayaka Mission's Research Foundation, Dean to be University Salem, Shri N.D. Chandrasekhar Sir, to deliver the inaugural address, iNEEBA 2024.
Respected Chief Guest, Dr. RIGET, Director, ARCI, Hyderabad. Respected Guest of Honor, Professor Dr. Myung-Chon Choi from Gyeongsang National University, South Korea. Respected Director, Mr. N. Ramaswamy. Respected Professor Dr. P.K. Sudhir, Vice Chancellor. Respected Dr. A. Nagapal, Registrar. Respected Professor Anbergen, Principal of VMKV Arts and Science College. Respected Head of Institutions from Constituent Colleges of Vinayaka Research Foundation. Respected administrators, distinguished participants, honored speakers of iNEEBA 2024, faculty members and staff of Vinayaka Arts and Science College, distinguished guests and my dear students, a very good morning to one and all. It's my privilege and honor to be part of the inaugural function of this prestigious SERB-sponsored Indo-South Korea, Thailand 4th International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications, iNEEBA 2024. At the outset, I would like to thank our international collaborators, Gyeongsang National University, South Korea, and Chulalongkorn University, Thailand, for their unwavering support and collaborating in organizing this prestigious event. I would also like to congratulate our principal, VMKV Arts and Science College, Professor Dr. Anbergen, and the organizing committee for hosting this conference and making extra efforts in making this conference a grand success. This international conference is only possible with the strong partnership between VMRF, GNU South Korea, and Chulalongkorn University, Thailand. The conference has established itself as a premier platform for knowledge sharing, innovations, and collaborations in the field of nanoscience and nanotechnology. iNEEBA 2024 will be an enriching experience with technical sessions, keynote speakers, and panel discussions focused on cutting-edge research and applications in energy, environment, and biomedical fields. We are proud to have Dr. R. Vijay, Director, ARCI Hyderabad, as the chief guest, who has kindly consented to inaugurate this international conference. Sir, your valuable presence will give all the participants and students great inspiration and will motivate them towards innovation and research. The previous iNEEBA conference have yielded esteemed publications, and this year the event promises to be equally insightful. We acknowledge the esteemed speakers, researchers, and participants who have come from far and near to share their expertise and contribute towards the success of this conference. We acknowledge the generous sponsorship of Science and Energy Research Board, SERB, Government of India, towards this international conference and express thanks for the continued support. With the increase of global warming and depletion of natural resources, building a sustainable future is the need of the hour. The potential of science and technology is boundless, and our collective effort in research, development, and application will continue to shape the new world. In these 2 days, we shall have the opportunity to explore advanced research in nanoscience and nanotechnology through enlightening discussions and collaborations with the subject experts. This is a great opportunity for the students to interact with national and international researchers and get to know the latest technologies and their applications. Thanks to all the members who have worked tirelessly for the success of this event. My congratulations again to Professor Anbaragan, Principal of VMKV Arts and Science College, and the entire organizing team for the elaborate arrangements for the 2-day event. I am sure the conference will be a fruitful and exciting to all the participants, and we are looking forward to the outstanding contributions to the society from this 4th International Conference, iNEEBA 2024. Thank you, one and all.
Thank you, sir. Energy and persistence conquer all things. Sir is a professor of chemistry at Gyeongsang National University, Republic of Korea. Sir completed his PhD in chemistry at the University of North Carolina at Chapel Hill, USA in 2006. He has received numerous national and international awards, including the Top 50 Environmental Technology Award by the Ministry of Environment 2014, KCS Young Physical Chemist Award 2015, the Gyeongsang Award for Excellence in Teaching 2016. He is also the member of Gyeongsang Hanlin Academy 2020. We are honored to have you here with us today, sir. Now I welcome Professor Dr. Myong-Yong Choi, convener, iNEEBA 2024. Director, Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea, to present the conference highlights iNEEBA 2024.
Thank you very much. A very good morning to one and all gathered here. On behalf of the Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea, I extend my warm wishes to one and all gathered today for the international conference. It gives me immense pleasure to jointly organize the Indo-South Korea-Thailand 4th International Conference on Nanoscience and Nanotechnology for Energy, Environment, Biomedical Applications, along with the Vinayaka missions, Kirupananda, Variyar Arts and Science College, a constituent college of Vinayaka Missions Research Foundation, deemed to be universities, Salem, and Chulalongkorn University, Thailand. The aim of the iNEEBA 2024 is to provide an effective platform for the academicians and researchers and startups and industrial participants to connect, discuss and exchange their research ideas and explore appropriate future strategies in the field of nanoscience and nanotechnology. In addition, I believe that it would provide an opportunity for the potential scholars to develop and enhance their research skills, and also it would lay an emphasis on the processing of new economical smart materials and facilitate its applications to the next generation of researchers. The iNEEBA 2024 includes 4 technical sessions with keynote lectures, 16 invited talks by distinguished speakers, and more than 250 contributed papers from various countries, South Korea, India, and Thailand, and Saudi Arabia, and UAE. And the contributed papers are presented in 6 parallel oral sessions via physical and online mode. Young scientists' research and accomplishments need to be recognized by the academic community and the rest of the world. And offering a Best Presentation Awards presented by iNEEBA 2024, it intends to do just that by honoring promising scientists who are actively engaged in R&D and produce high-quality research. Before closing, I must extend my further thanks to Vinayaka Missions Research Foundation Management and Chulalongkorn University, who greatly helped in organizing this conference. The vision of our university is to keep pace with the world, so active GNU. One of the goals of our institution is to strive for excellence in research specializations and blending. I strongly believe that the iNEEBA-2024 is one of the outcomes of the goal of our university, which is also in line with our vision. So it is heart welcoming, warming to a part of this conference, and I'm sure that this conference collaboration will pave the way for the extending research collaborations between the three institutions and extend research support to each other. So let us together embark on this virtual journey and use the online platform for the knowledge sharing and enhanced research networking. And thank you very much for your attendance. Thank you.
Thank you, sir. True leadership is about creating a vision that others are inspired to follow. Sir has over 3 decades of professional experience and more than 2 decades in academic and administrative roles in the field of homeopathy and health sciences. Sir has introduced many digital examination systems in health science disciplines and has published various scientific articles in national and international journals. His achievements has been recognized with Dr. Mahendra Singh Memorial Best Administrator Award, Kolkata 2014 and National Rejoice Ayush Award, New Delhi in 2019. Currently, he is the Vice Chancellor of Vinayaka Mission's Research Foundation, deemed to be university. It is my honor to welcome our Honorable Vice Chancellor, Professor Dr. P.K. Sudhir sir, to deliver the Presidential Address.
Respected chief guest of this today's function, Dr. R. Vijay, Director, International Advanced Research Center for Powder Metallurgy and New Metals, ICA Hyderabad, India. Respected Vice President, Mr. N.V. Chandrasekhar, respected Professor Dr. Myong Choi, Director, Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea. Respected Director N.V. Rangasamy, our respected Registrar, Professor Nagapan, our Principal, Dr. Anbergen, invited guest, head of the institutions of our constituent colleges, head of the departments, university officials, faculty members, distinguished delegates from all over India, non-teaching and support staff, press and media, ladies and gentlemen, a very, very good morning to you all. I am extremely delighted to be the part of this distinguished conference and congratulating Vinayaka Mission's Kirupananda Variyar Arts and Science College on hosting SERB-sponsored Indo-South Korea-Thailand 4th International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications. This event is organized on building upon the success of our previous conferences, 21, 22 and 23. I extend warm greetings to our international partners, Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, Republic of Korea, Department of Chemical Engineering, Chulalongkorn University, Thailand. This collaboration has been instrumental in making iNEEBA, a flagship conference in the field of nanoscience and technology. The theme of iNEEBA-2024 focus on the energy security, environmental sustainability, and biomedical advancements. Our previous conferences have resulted in publication in esteemed journals. It's a great achievement. I congratulate the Arts and Science College, the principal and the entire team taking this effort from 2021 onwards on a very sustainable model. Vinayaka Mission Research Foundation deemed university has come out with our 2030 vision document with collaboration and partnership as one of the very important elements. It has been proved from time to time, institutions cannot survive in isolation. Institutions and universities should have collaborations and partnership with reputed institutions in India and abroad. Last couple of years, we have strengthened our research labs, research support system in terms of equipments, infrastructure, manpower and finance to upgrade our research outcomes. I'm extremely happy to say that we have crossed 1,000 indexed publications in the year 2024 in the October itself, and we are targeting 1,500 publications in the coming in this end of the calendar year. I'm extremely happy to note that our faculty members are seriously involved in collaboration and collaborative activities. We have a very good collaboration with the Indian Institute of Science, Bangalore, and NIT Trichy. And also we are looking for international collaborative partners for further research activities. I must thank to the partner, our collaborative partners of the university, inviting our Dr. Anbaragan as a subject expert to their university. Thank you, sir. Conferences and seminars are platforms for knowledge sharing and knowledge change. My dear participants, and I understand most of the participants are younger generation below 30. Government of India has come out with Anusandhan National Research Foundation with every year 10,000 crores funding and attracting the young scientists for research purposes. It is my wish and it is my request to the younger generation during their academic career and immediately after academic career, show some propensity to the research and research outcomes. I'm sure these 2 days deliberations, today and tomorrow, for the participants, I'm sure there will be a serious takeaways and things will take to your respective institutions and explain to the people and come out with the new proposals. Thank you very much for this opportunity. Thanks.
Thank you, sir. Next, with immense pleasure, I welcome a man with 30 years of experience in research and development in material sciences and processing technologies. His primary research interests include nanomaterials, high kinetic processing, mechanical alloying, oxide dispersion, strengthened steels, supercapacitors, biomaterials, additive manufacturing, and hydrogen storage materials. He has executed about 15 prestigious sponsored projects from DAE, DRDO, DST, MNRE, and international projects of IGSTC and GITA as a lead principal investigator. With 25 patents and 55 publications to his credit, his achievements are vast. His accolades include the DAA Indo-US Fellowship, Engineer of the Year Award from Institution of Engineers, and the Distinguished Researcher Award from FTCCI. He is a fellow of Institution of Engineers, India and the Telangana Academy of Sciences. Currently, Sir is the director of ARCI. It is my privilege to welcome the guest of the day, Dr. R. Vijay Sir, to address the gathering.
Good morning, everyone, and respected Vice Chancellor, Professor Sudhir, respected Vice President N.V. Chandrasekhar, and the convener, Ambazagan, and then the guest of honor, Myung Choi from Gyeongsang National University, South Korea, and of course other dignitaries on the dais. And I'm overwhelmed and then delighted to be here as a chief guest for one of the international conferences on energy, environment, environment and biomedical applications. I know when you're looking at nano materials, it's being, a very buzzword in the last 20 years. People talking about nanomaterials, nanomissions, and then other things. I think you're all aware that, when you are going into the nano, see, from a macro size to the micron size to the nano size, the properties, and then in terms of it's a thermodynamics, properties completely change, and then you can use it for different applications. You can make it with the small components, you can miniaturize. And we have seen the industrial revolution in 19th century that's completely changed our life. And we have seen an IT revolution in 20th century that also changed our lives. And then all of you arrived because of all these gadgets and then smartphones, and most of you are getting disconnected with the functions and then the speakers and then what they are seeing, and that's because of your IT revolution, that has actually, brought you all together, but it also created a disconnect, personal disconnect amongst ourselves. But this 21st century is the materials revolution. And in order to have a good quality life and then good comfort, you all need materials. So for example, I'll tell you a couple of examples. One of that is when our childhood, probably when I was childhood, and then most of you might not have seen that, but there used to be an ambassador car at the time. And now the cars, you see, the Innovas and then very high-end cars, it gives you very comfort driving, and then very comfort, the pickup, the speed, the maintenance, then the endurance levels of those vehicles. That's because of the change and then the revolutions in the materials. And we are demanding, the common person is, it's a very high demand on the quality and the comfort levels. And another example I'll tell you is an air conditioners, refrigerators. These are all becoming more and more compact, and then we are all looking at your mobile phones. You might have seen the phones which are there, all the transistors, all those gadgets. All those things, because all come up with the materials, whether it is in a communications or computer science or it is a manufacturing industry. So everything depends upon the materials, and then which has a very high specific strength, so that the volume and the weight can come down for a given size, given volume. And the other aspect is also miniaturize your aspects. So that's what, nanomaterials has taken a very significant shape. And it's one of the things is, it's very, very important in the energy. We are all moving to the when we are making transition into a clean energy. Our Honorable Prime Minister has made a statement that by 2070, then our carbon emissions will be net zero. And we are all working towards that to develop an alternate technologies and then improving the efficiency of the existing solar energy harnessing, and also looking at an hydrogen economy in terms of move away from the fossil fuels and then coal or the crude oil, which India is majority depending upon the other countries. So we have a vast availability of water. So you convert the hydrogen, and because presently the hydrogen conversion from water, even though the thermodynamically the potential is only 1.5 volts, you have to give it around 2.03 volts to split hydrogen, water into hydrogen and an oxygen. So typically, presently, alkaline electrolyzer, takes around 50 units, energy units, 50 units of electricity to produce 1 kilogram of hydrogen. So that's converting into around 500 rupees a kilogram. And then that's very, very expensive. And what one of the key factors is, you create a catalyst, electrocatalyst, so you cannot reduce the potential. Still, the over potential is needed to split water. But what you can do is you can enhance the kinetics. So for a given unit of energy supply, you produce more quantity of hydrogen, so thereby you reduce the cost per kg of production. So we are targeting about something like 10 to 20 units per kg of hydrogen, and that will be possible only with the nano electrocatalyst. Because why I'm talking about nano, you all know that it's all surface and have very high surface area, and you can always load very small quantities, so you don't have to spend much money. And then volumes, you cannot have a penalty on the volumes. So you can always do that. That's one of the aspects you can look at it on the hydrogen energy sector. Probably in this thing you might be discussing about. I think that's a very happening thing. And if somebody comes up with a electrocatalyst to having a good performance, he will be a billionaire. He will be the world. So that's a kind of a thing, we have to cutting edge technologies, we have to think about it, it's a kind of an out of the box thinking. You have to do it to come up with a more not only to serve the purpose, but also economically viable to produce and then deploy in the market. So the next thing, it's going to be an environment. You all know that CO2 is the biggest problem. We have committed to reduce the CO2 emissions, not only in the vehicles but also in the factories. We are transitioning towards changing the gasoline engines to the electric engines or the hydrogen driven engines, all the vehicles, so that you can reduce very diffused CO2 emissions on our roads. But still, right now, when it's going to take long time, but still we have to depend upon our energy needs from the fossil fuels, especially thermal power plants, and that is the biggest. Around 80 to 85% of our energy production is coming out from the thermal power plants presently, if you look at it. So one of the things is, you need to convert that CO2 into any other useful product, and that's a challenge. So you can directly make CO2 and then store in the form of liquids, or use it in form of chemicals to produce any other things. People are working on from the methanol and then other aspects. But I feel I'll throw a challenge that, if somebody works on convert CO2 into a solid carbon materials, and that is very, very environment. So we know every material, even our human body contains a carbon, and then other environment needs a carbon. So you can throw anywhere. It's useful to the Mother Earth. So you don't have to dispose of, you are not creating that. So that's another very, very, very important thing for the environment. And then other thing is, biomedical applications. We are talking about controlled drug delivery systems for carbon aerogels. Then you're also looking at very miniaturized implants, biodegradable implants. You all very much aware that when you meet with any accident, the bones fractures, then you have to get it operated and then put an implants, plates and then screws. So presently very biocompatible stainless steels or the titanium alloys or the cobalt based alloys are being used, and they are all permanent and they remain permanently in the body, and then also leading to the leaching of some of those unwanted elements, causing a lot of problems, thrombosis and other things. So you need to go to the second surgery. So the next generation implants which are coming up is a biodegradable. So that means, for any bone to get a full strength, it needs around 12 months. So you don't have to be, the implant need not be there after the 12 months. So what this biodegradable implant is, it stays there for the 12 months and then it starts trying to degrade and then dissolve in the body fluid. And then after 24 months, it will completely dissolve and then you don't have any implant. So one of the things, nanostructured bio implants will be, because you all know that, as you are going, the grain size comes down, the strength goes up because of the Hall pitch relationships. So when you have a nanostructured bio implant, two things can happen, because you are all chemistry people, I understand, most of them are. Then one is because of high grain boundary area, the corrosion rates are very faster, and because of the finer grain size, the strength goes up, so you can miniaturize and then you can make very, very small implants. And then the nano, it serves both purpose. It improves the degradation process, and at the same time it will also miniaturize. So all these topics are close heart to me, and I belong to ARCI, which is a Department of Science and Technology Institute, and we bridge the gap between that. Many of you do the difference between invention and innovation. Anyone knows between invention and innovation? So you find something in your lab, a new molecule or anything, that's called an invention. But when it is commercialized and when it's deployed in the market, and then when we start making money out of it, so it's called an innovation. And then to reach from invention to innovation, you have to cross a valley of death. See, it's valleys, it's between two mountains, two hills, and then you are on the first hill which you have done, invention, research in your lab, and then you come up with a very new molecule, and then you say that, hooray, and then I got it. But you file a patent and then other things. But obviously when you want to make money, the industry requirement is on something, so it is sitting on the other hill. So until unless you cross this valley, you don't reach there, and then you don't make money, so it will not convert into an innovation. So what it does, what we do precisely is we bridge that gap. We bridge that gap between that invention and then innovation, and then we allow the people, we handhold the people to cross that valley without dying. So that's what we do it, and then to do that, it needs a expertise from multidisciplinary expertise. You need it, and we bring in different people for packaging and then manufacturing, and then finally selling it. Ultimately you have to sell it. Either it should be completely even though it's a disruptive technology, and if it is not affordable and then not reachable to a common man, it dies. No one buys it. So you need to keep all this in mind, and at the same time, if it is a new technology, the public awareness, the adaptability of the people. Sometimes people are not adapting to the technology, it dies. So adaptability, public awareness, and then economic viability, all these factors, and then ergonomics. That's another thing. If you look at it, the scooters, you might have seen that earlier Bajaj Chetak was once upon a time a very famous scooter. Now it's almost vanished. So you don't find the scooter, because what happens is, you come up with a very ergonomic, sleek designs, and then the public adaptability was there. So it has a natural die. Until unless you change, you reform yourselves, you are going to die. This is kind of a competitive environment, even in an education. So you have to be very innovative. And then where in ARCI we do that thing, we work on nanomaterials, we work on hydrogen and electron batteries, then fuel cells, solar energy. Then we also do that, all that laser processing, additive, metal additive manufacturing, then laser machining, micro machining, drilling, all those processing. We have a carbon materials, carbon fibers, then ceramic materials, so catering to the civilian applications and also strategic sector. So some of the, I'll tell you before closing it, some of the examples what we have commercialized or nano powders, nano suspensions for the textile finishes. So if you get into any Decathlon or any flying machines or Wrangler showrooms, you find with a self-clean or a sun clean or sun wash, all those things you buy it. I mean, that's all with the technology what we have developed with a nano silver, antimicrobial activity, and then N9 undergarments, socks, so they don't stink, and then all the sportswear and other sun wash with the nano titania with a photocatalytic activity, self-cleaning activity. So these are all commercialized and then being available. Then is our battery materials as a cathode materials, lithium iron phosphate with a, you see that intricacies, it should be a nano size particle, and then you need to have a 3 to 5 nanometer carbon coating, because to improve the conductivity, electron conductivity of this material. So that's the kind of a thing it is done, and then we have transferred that kind of technologies. We have extensively working on solar energy, absorption coatings, self-cleaning coatings, all those things we have transferred those technologies. And then coming back to the, I'll take one more minute, coming back to the opportunities. So government is also looking at, encouraging, you are the future of our country, and government is encouraging the young students to bring into the research, bring into this, the entrepreneurship, the innovation concept. So encouraging to you be more, giving you opportunities, exposing you to the better places, better education facilities, and then better research facilities. In terms of so many gatherings, and then more, next, the other important thing which is coming up is you might have heard, or if you do not know, please note down that there is a program which is coming up, is an India International Science Festival, which is coming up from November 30, 1st December 1 and 2nd, which is being held in Guwahati. And that is being organized every year. If you can search India International Science Festival, and that is precisely meant to showcase our science and technologies opportunities to the students, both from the school and college students. And each college they sponsor. If you apply 2-3 people from each branch, they extend that sponsorship, and then they make you to visit those things, and then take that opportunity and then see it, and then get connected with the people, the facilities, so where you can have your future contributing to the Indian science and then technology. The next opportunity government is working on is creating that kind of a culture of entrepreneurship. So many startups are coming up. Government is encouraging. If you come up with an idea, government is giving seed funding of around 8 to 10 lakhs, and then connecting with proper research institute to actually discuss whether this idea is really doable or it is a crazy idea. So that kind of mentorship will be available. Make use of those facilities, and then Department of Science and Technology is doing that. And one of the things probably you may implement, think about it, is, IIT Hyderabad has come up with a facility that, when a student joins in a BTech program and after second year, they may give that if he comes up with an idea, they will extend a leave. They will allow them, and then they will attach him with a professor to mentor him, so that he can go out and then spend on his idea and then make some things and then start his own company and then be a businessman and then do that 2-3 years and then also come back and then join and then get his degree. So that's the kind of facilities they are all looking at it. And if you look at it, the startup ecosystem is very good. I'm very happy that the young people, when I just passed out from my BTech in 1990 and then MTech in 93, I have no other option except joining a government job, either a public sector or any other thing. But now, when I tell my son, he has done his computer science in BTech from IIT, then I tell him, he joined a campus job, but then I tell him that, you don't have to do a 9-to-5 job like me, but you can have, more opportunities, you can have your own company, so that, you have two things, when you have your own company, you give, tangible benefits and then intangible benefits. Tangible benefit is, for you and then how much money you are making. But then the intangible is, how you are helping and then how much employment you are creating and then how much tax you are paying to the country, and that's an intangible benefit. So in terms of that, you are helping your country, you are helping your society, and then you are helping your fellow colleagues, creating the jobs and then creating an opportunity. So young people, you have many opportunities. I request, with an idea, you can have companies. And then we are looking at a manufacturing hub in the world. India is going to be a global manufacturing hub, not only manufacturing, but even in the service, anything. So we should be the torch bearers. And then I've looked at statistics. By prior to 2014, if you look at the number of startups, it was only around 700 to 800. And now in 2024, the number of startups are around 170,000. So that means, the interest is there, the zeal is there, the enthusiasm is there, and then there is a right kind of an ecosystem for a company, for young guys to start their companies. And then I want at least, you people, when you complete your education, come with an idea, and then you can have your own companies, and then there are many people to support, and then money is available everywhere. So there is a lot of money available in the country, and then people are ready to invest, and then they are looking at for a right opportunity. I'll tell you two examples. One of the companies, which a startup company, which took a technology from us, and then, he might have spent around 10 crores, but then when he has evaluated, the company is, valuated at 700 crores. This happened in two years. And then the other aspect is, there is another company which has got turnover is around 35 crores, and when we went for a public issue, and then it was subscribed for 13,000 crores. So don't think that money is not available. There are investors are available. There are venture capitalists are available. So money is available. So they are ready to invest on that. So what you need is an idea. What you need is an entrepreneurship. And then what you need is in how you present yourself, and then how you make it into a good proposal, good company, and then where you can produce products, and then you can contribute to the Indian economy. So all these things, why I'm telling about it is, we are not told, when I was student, I was not told anything. What I was told is, you study, you follow, you attend the classes, you follow the subject, and then you read this book, and then you write this exam, and then you get good marks, and then you get out of the college. That's all, it was told. We are not told anything. But now, you have a different system. We are in a different position where you can do anything what you want. You have the freedom, you have the ecosystem, what exactly you have, and then the parents are also more educated, more knowledgeable, and then more supportive. And then that kind of an ecosystem is available from the poor parents, from the teachers, from the government. So all those things is available. So why I'm telling is, if you do like this, we will be becoming in global players, global torch bearers, and then global leaders in every field, what we do it, and then we go back to our own Indian ancient history. If you're looking at 3rd century BC, 4th century BC, India is a very dominant economy. And like that, we will be going, again, we have to reach to that level, and India should be a superpower, and we are looking at a Viksat Bharat by 2047. So all these things, doesn't come in overnight. All those things will come from you only. You are the young people, you have a lot of energy, and then you have a lot of ideas. And what we can do is, we can only discuss, tell you, give you and mentor you, and then show you a direction, but you are the torch bearers. And if you have all those things, India will become really a developed nation and a superpower by 2047. So thank you very much.
Thank you for your words of wisdom, sir. Coming together is a beginning. Keeping together is a progress. Working together is a success. The world is a mosaic of ideas, and together we complete the puzzles of progress. It's a memorable moment to release our international conference proceedings of iNEEBA-2024. May I request Sri N.V. Chandru sir, Vice President of Vinayaka Mission Research Foundation, deemed to be university, to release the proceedings to our chief guest, Dr. R. Vijay.
Thank you, sirs. Be thankful for what we have. You'll end up having more. If you concentrate on what you don't have, you'll never ever have enough. Sir is currently working as Research Professor, Brain Pool Fellow in the Department of Chemistry, Gyeongsang National University, South Korea. His current research focuses on the development of electrocatalysts for the production of energy-saving fuel and value-added chemicals. Professionally, Dr. Tirthagiri sir serves on the editorial board in Bioengineered and Science of Advanced Material journals and as an associate editor in Chemical Papers journal. Sir has published 175 referred papers in high-impact international journals, edited 2 books for Elsevier and 1 book for RSC publishers, contributed 20 book chapters and 4 patents. And Sir has also delivered several invited keynote plenary lectures at international conferences and academic institutions. Now, I request Dr. Tirthagiri sir to deliver the vote of thanks.
So, good morning to all. First of all, I would like to thank the management of Vinayaka Mission and organizer of iNEEBA-2024 for choosing the wonderful and important, especially the current needed topics. Professor Vijay has briefly mentioned about the current needs of renewable energy and revolution in the science and technologies. Yes, day by day, the needs for renewable energy and clean environment is keep increasing along with the population and industrial development. So most of the energy currently we are using from the fossil fuels, as Professor Vijay mentioned, 80 to 85% of fossil fuel we are utilizing for the our needs. So we need of alternative resources. That was the renewable energy resources. So what happened if we use fossil fuels? So fossil fuels like, for example, petrol and diesel, which are the most consuming in the vehicles, transport system. So these are all the like a natural resources. We don't know how long we can use these natural resources. So we need of alternative resources. And another point is these petrol and diesel emit the toxic gases, CO2 gases. So we need to avoid the environmental pollution. These are the main topic of, the present conference. So these, clean energy production, especially water splitting. He mentioned about the water splitting, and I think the Professor Myung Choi is the first keynote speaker. He will explain more detail about the clean energy productions. So as a science students, what we have to know, whether can I replace this transport system, petrol and diesel engine, by electrical vehicle? Is it called renewable technology? No. As a science students, we need to see how this electricity is produced. This is what our major focus. So that is what we are studying and we are developing. So with this conclusion, I think we can learn at the end of this conference, we can know more about the needs of renewable energy and clean energy, environmental technologies. These we can learn it at the end of this conference. I hope you can enjoy these 2 days event. I wish you success and happy day. Thank you.
Thank you, sir. The power of national anthem unites us and fills our heart with love for our country. Let us end with this patriotic note. I kindly request all to stand for the national anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
A cup of tea is a cup of peace. Tea is a ritual and art that nourishes the soul. Enjoy life sip by sip. Kind attention to all the participants. Tea and goodies have been arranged outside of the auditorium. We request all the participants to come back to the auditorium in 10 minutes. Thank you. the most charming and exquisite Deputy Dean, Vinayaka Mission's Kirupananda Variyar Medical College and Hospital, Salem, Professor Dr. Deepthi Shastri Ma'am.
Asking if it is keen. Good morning, everyone. It's my privilege to introduce the first speaker for the day, Professor Myong-Young Chue. I've had the privilege of chairing his session last year on pulsed laser induced synthesis of clean energy materials. And I can't wait to see the progress of his research as he presents today's title, that is Advances in Pulsed Laser Process for Energy Conversion. Professor Myong-Young Chue is a physical chemist specializing in spectroscopy, laser photochemistry, and nanomaterials. He is a senior academic staff member at the Department of Chemistry at GNU, South Korea, where he teaches both undergraduate and postgraduate students. In addition to his teaching duties, he serves as the director of the Core Facility Center for Photochemistry and Nanomaterials and is the head of Graduate School of Department of Chemistry. Professor Chue earned his MS and PhD in chemistry from the University of Idaho and the University of North Carolina at Chapel Hill, USA, respectively. After his studies, he worked as a postdoctoral fellow at the Faculty of Science, University of Southern California, USA. He also had the opportunity to serve as a visiting professor at the University of North Carolina at Chapel Hill during 2013 to 14. His research team has developed numerous innovative techniques based on laser processes to characterize and produce a variety of metal nanoparticles, alloys, composites, and coordination polymers. Their significant contributions to spectroscopy, sensor technology, and catalysis are well recognized. Recently, they have also been involved in laser synthesis of functional nano and biomaterials for use in energy production and environment remediation. Professor Chue has held several editorial positions in prestigious journals, including senior editor for the Journal of Laser Applications, editor for Light, Science and Applications, and associate editor for E-Light, Environmental Chemistry Letters, Applied Physics, Applied Nanoscience, Chemical Papers, and Alexandria Engineering Journal. He has also served on the editorial board for the Journal of Hazardous Materials and Bioengineered and as a guest editor for Chemosphere, Environmental Research, Biomass Conversion, and Biorefinery and Environmental Pollution journals. He has edited a book titled oxide-free nanomaterials for energy storage and conversion applications for Elsevier, and another book titled Pulse Laser-Induced Nanostructures in Liquids for Energy and Environmental Applications for the same publisher. Professor Chue scholarly output is impressive, with over 250 referred papers published in high-impact international journals, 11 book chapters, and 6 patents to his name. He has delivered several invited keynote and plenary lectures at international conferences and academic institutions. He has served on several management committees at GNU, including as the director of the Center for Lab Safety and the director of the Center for Research Facilities and the department chairperson. He has also served on the scientific advisory boards of external scientific organizations. His work has been recognized with several prizes, awards, and fellowships, including membership in the Gyeongsang Hanlim Academy and the Gyeongsang Award for Excellence in Teaching, the KCS Young Physical Chemist Award, and the Top 50 Environmental Technology Award by the Ministry of Environment in 2014. Our accomplished speaker on stage, the stage is all yours, sir.
Thank you very much. Thank you very much for your very nice introduction. Thank you for all your attendance, and thank you, Professor Ambulagam, for organizing all this wonderful international conference, 4th in a row. And also thank you for all the people attendance here and all people online. And I'll briefly talk about my research using pulse laser ablations, and briefly talk about just whole stories. And later, Dr. Theatigiri will be giving these details of the stories. And okay, let's go. So since this is the 3-country organizations, laser is not working on the LEDs anyway. So this in Indo-South, Korea-Thailand, and we are all co-organizing this international conference, and here's Korea. So since you don't know about Korea, and we are the one of the major 8 national universities in Korea, in Jeonju, in southern part of South Korea, and this is the Jeonju. You can see this in this autumn. Dr. Ambulagam knows, as he was in a month ago. All colors in this autumn season. So in December it will be getting colder. So we have lantern festivals here. And I'll briefly show you about the GNU. And this is our national university in many degree program, doctoral and integrated masters in doctoral. We have the 7th largest nationwide in campus-wise in Gyeongsang province, in the southern part of South Korea. And we have lots of facilities. This is my lab, and using the core facility center, my students working on all these instruments while they're working, synthesizing it, and then characterizing it, applying all these things at the same time in one time. So this is another medical campus in Jeonju, and we have lots of variety of programs. So since this Global University 30, so you have to maybe remember, so this is very prestigious government funding program. This is a laser lab and same facilities of my lab members and XPS. This is the main gate of main campus, and later that's the core facility center on campus. Okay. Thank you very much. I'll just briefly show you about the core facility center in GNU. So another thing I just mentioned, Global 30, that's the one in Korean. Sorry about that. But that what governments, Korean governments, is facilitating, supporting 30 universities out of 363 universities in Korea. Only 30 universities, they're supporting lots of funding, especially here in Jinju, here, so where GNU is located. Here, right next to cities, Hacheon, Jinju, we have a first NASA, Korean NASA, launched this year for the first time. So we are very excited, and the local 30 university was selected based on this aerospace defense system in Korea. So of course, in India is a huge development in aerospace, but we just launched it. So we are really excited to see and do research collaborations between the CASA with the GNU and also Core Facility Center. And based on that, we have some benefits. Here's a local used to be domestic airport. Now it will become to the international. So I'll be more beneficial later once I go to the international conference. Much better, not going to Seoul or Busan. So, and this is my lab. Maybe some of you guys know this. And this is the lab I'm having here. So that once they do the experiments in laser room or open lab, and they just go to the FESM, XPS, and other instrumentals at one spot. So it's a one-step experiments they can do. And more specifically, we can do one step on on-site characterization and in one lab. So it's much easier for my students to do the characterizations and also synthesis and application. And specifically, specialized instruments, we have in-situ multispectral analysis using lots of different laser sources for the spectroscopy, and also SEM and XPS, low temperature photoluminescence studies. But in addition to this is the new one that I got the funding from the government this year. This is XAS, In-situ Cryogenic X-ray Absorption Spectrometer. This is a $3.5 million machine will be installed in the Core Facility Center, so that we don't have to wait for the other a long queue from the synchrotron and other works. So basically, what I'd like to show you is a lab tool. This is a lab scale, so because we want to use a synchrotron, but there will be a huge queue. So we have to wait long time for the experiment to do this. So, but once it's settled, installed in my lab, so it will be much easier. We can do the X-ray absorption of all kinds, covering most of the elements, and also has a light patent in X-ray sources as high power. It's mostly equivalent to the, not equivalent, but it's most comparable to the synchrotron light. So, and this is the first machine and instrument in Korea for the in-situ and operando electrochemical cell. And this is the world first instrument using cryogenics. So its temperature goes down to 4 Kelvin. So that's why, we have a large collaborations between CASA, Korean NASA, so they want to have extreme condition studies, ultra low temperature and out of the atmosphere. So we like to use this cryogenic, and so that we can do further studies on extreme conditions, especially ultra low temperature, and also it goes up to the 1000 Kelvin too. So basically, it's like a synchrotron-like performances in the laboratory XAS system, and we can do in-situ in operando electrochemical cells and cryoset. So temperature goes down to below 4 Kelvin, up to ultra high, about 1000 Kelvin. So the everything goes down to 4 Kelvin out of space, and then once the sun rises, the temperature goes really high temperature. So we can cover all these temperature ranges. And also energy ranges, so it's mostly metal in periodic tables, we can cover most of them. So we have a collaborative from the US and China and of course in Thailand. And we have all collaboration from Chula and Siam Photon and Co-Facility Center. We can utilize these instruments for the further international collaborations. So you're welcome to ask any, it's collaborative work or any sample acquisition, characterization acquisitions. We are very welcome. So the mission of my lab is the world-class photochemistry lab for specialized in energy, environment, and sensors. So we mostly use lights, like laser sources and microwave or solar lights to generate nanomaterials. And then we can analyze this right away at the characterization, all different, using the core facility center instruments. And then we can apply this to the all renewable energy and environment or sensor applications right away, especially hydrogen energy, photocatalysis, green chemistry things. So I'll briefly go on to the why, the way we use laser systems. We use, as you know, there's a conventional, synthesis, nanomaterial synthesis method. Top down is just breaking down of larger pieces into the small pieces. Or bottom up is using the pulse irradiation without lens. That's when we use lens so that we can focus to the surface of metal, so we can do the pulse ablation in liquids, not in the vapor system, the vacuum systems. This is the irradiation without using lights. So basically we can do the photo reduction to generate the nanomaterials from the ions, metal ions. So there's some examples we can do right away. We can just shine the laser to generate nanomaterials. This is gold and silver things. It is very easy and very fast without just surfactants or other things, reducing agents. So it's mostly byproduct free and eco-friendly system at the ambient temperature. So we can do this. So we can produce lots of different varieties of nanomaterials using the pulse laser systems. So first thing I mentioned is that this is the one that you can see this. If we ablate to the nickel place, the most global minimum structure, stable structure is FCC. So as we know from the chemistry, general chemistry book, and mostly we can get FCC1, and also, but HCP, hexagonal closed pack, is a metastable state, so it cannot be obtained, usually in wet chemistries. And we can see, depending on different solvents we used, and in PLAL system, we got all different kinds of ones. But one of my graduate students did it, she did it, and then she did it one more, primary and the secondary ablations. She got very selective, the producing of different these phases of nickel nanoparticles. It's methanol only pure FCC, and acetonitrile in the D case only HCPs are formed. So it was really strange to see this. Why is it happening? So we just anyway produced it, published it anyway. I don't know. We didn't know at the moment. Maybe some thermodynamic or the kinetical control in the process of pulse laser ablations, because the plasma plume produced nanoparticles. It may be dependent on the solvents used. So we checked with the different solvents, and only specific heat has some tendency. Now others are all just scrambled around. So before we go into that, let me see the time sequences for laser ablations. When shine the laser, plasma plumes, happens. It dies away at about nanoscale scales, and at later shock waves happens, and then light spots and decays around 1 microsecond. And the one we are interested in is here is cavitation bubble formation, so that the nanoparticles are formed in the cavitation bubble, we can monitor this in microsecond scale. So what we did is a cavitation bubble in methanol or different kinds of ones. Then you can see the methanol and acetonitrile, two different phases. So the difference is you can see that low specific heat where the acetonitrile has its dramatic volume change. So volume change really fast, so that it cools really fast. So the high temperature they form the nanoparticles cools really fast, so that it forms a metastable structure nanoparticles. Instead of this, they slowly evaporating, slowly cools down. It goes to global stable FCC structures. That's what we observed after 8 years later. And then we did, since we measured these TM studies, we found this certain surface of these graphite carbon layers formed. Since we shine a single shot of laser produces layers of graphite carbons. So it matches exactly the same D spacings of 3.35, which is good agreement with the 002 planes of graphite carbon. So it's graphite carbons formed. So what we suggested is maybe depending on different the solvents, we can produce different kinds of nanoparticles. Okay, so then we apply this to the gold nanoparticles, also has graphite carbon layers. The carbon layers coming from the source, solvent source. Solvent decomposed, and then they form the graphite carbon layer on the surface. So that we can control this using acetonitrile 100%. Here is water 100%. We can see the ratio of the solvent mixture. Maybe we can control the gap between two gold nanoparticles. So that's what we did. And there's specific characterizations, and this by using the sulfate enhanced Raman spectrometer. So I don't have to explain in the land of Raman here. And you can see that AN30% of acetonitrile has largest source effect here, and also it matches with these simulations well. So that's how we controlled the gap between two metal nanoparticles using the different ratios of the solvent mixtures. So another thing what we did was using different solvents. Urea has a nitrogen source. So we can deposit or the doped nitrogen onto the surface of zinc oxide. So what we did was like a photocatalytic activities of rhodamine B, very simple thing. Excuse me. And then we applied this photocatalytic activity to the zinc oxide, the nitrogen doped. So it shows almost 98% degradation under the solar light in a very short time. So another thing, in the case of copper, so what happens? It's a little different, depending on different solvents. As copper oxide nanorods, instead of the spherical nanoparticles, here is a copper cyanide, is metal organic complexes, instead of the graphite carbon layers. So it's different with nickel case. Nickel case mostly spherical nanoparticles. So what's happening? So we wanted to try these specific nanomaterials to the reduction of the aromatic nitro compounds, like 4-nitrophenol to 4-aminophenol or nitrobenzene to aniline. So it's copper oxide and copper graphite carbon layer core shell structures shows the best efficiency using the UV spectrometer. We characterize with SEM and images with these XRDs. And later, so you may notice that these nanoparticles not homogeneous. So we applied it. How about using sono? Sono effect may affect this homogeneity. So you can see here nickel particle PL without sono and with sono, it's much homogeneous. So that we can characterize this. We can produce homogeneous nanoparticles within sono, and also it gives a better efficiency in hydrogen evolution reactions. So. And then another thing we tried it with alloys. So we shine the laser to the gold and platinum. We can produce gold platinum alloys. This is theoretical studies, and then we can apply this to the hydrogen coupled water electrolysis, and especially so OER, as Dr. Vijay told about, OER has 1.23 over potentials. We can reduce the energy using the hydrogen oxidation reductions, and we can save energy for generating hydrogens. So the detail will be given by the Dr. Siatagiri, or I don't know whether he's saying or not. But another thing, I would like to go on to the more likely about the production of different kinds of materials. So we use nickel, cobalt, and copper to the left, and using BTC, benzene tricarboxylic acid, BTC, and we get different structures. Copper case, octahedral structure, and cobalt, hexagonal, and nickel is seed-like structures. And we characterize all these, and then we apply to the HER and OERs and overall water splitting in the case. But it turns out to be that cobalt has best efficiency. We thought we think that this is like cobalt has large available, the active centers and also various oxidation states or, spin states. So it can generate more active sites compared to other metals like cobalt, just copper and nickel case. Another thing we wanted here, we didn't know what's happening in intermediate, when the reaction goes. So we applied it in Raman. So when the reaction goes, we can monitor the Raman so that we can check, we can just find out the intermediates. So in the case of these like a cobalt case, now here we use different solvents. So different solvents produces different materials, cobalt phosphate, oxide, cobalt sulfide, and we use in-situ Raman, and we can distinguish while applying this, and we get the cobalt oxyhydroxide is increasing. So that's the key intermediates for the reaction of these HER, OER studies. So here is OER. In the case of here, cobalt hydroxide is key intermediate in HER case. Later, so another graduate student, Shriyanka Naik, he did the LDH studies using pulse laser ablation in liquid, and so we got this the laser ablation technique to generate LDH, and then we get some help from the DFT people and DFT calculations we got, and then we using this in-situ Raman spectrometer, and when we analysis of in-situs and operando studies, we got this, which one is a key intermediate in the reactions of OER or HER mechanisms studies. So later on, that's another thing. We wanted to use LDH to produce palladium is at the nickel cobalt oxide for the overall hydrogen splitting case. So in this case, it shows excellent bifunctional electrocatalytic activity both in HER and hydrogen oxidation reactions. So it shows best efficiency in bifunctional, so that we can just use all the characterizations using different at different voltage we applied, so we can get into IR Raman studies, and we can check whether this cobalt hydroxide or nickel oxyhydroxide is the key intermediate during the OHER, OER condition, HER and hydrogen oxidation reactions. So you can feature in front carbon in ACS catalysis. And another thing, we use laser to the MXene. It's like a 2D layer system. And we shine the laser. First time I thought, oh, it can produce the platinum onto the surface of this MXene. But later it turns out to be all spherical particles. So what happened? So I don't know. I mean, so that's why we further studied, and actually the laser reshaped and shined a high power laser and then reshaped the MXene to produce the titanium dioxide inside, and the surface is a TiC, titanium carbide, and platinum is coated onto the surface of it. So that we know that PTC is good, best material for the HER, and so we wanted to try these electrocatalytic and hydrogen evolution reactions. It's pretty compatible with the PTC. So that the left is pinky, orange color is PTC, and the other, right-hand side one was this material. Okay, since titanium dioxide has good photocatalytic efficiency, we use sunlight. So then it shows better efficiency than the commercial PTC. So, and also with excellent stability for more than 50 hours. So it's covered in the ACS Nano. Another thing, we use the high entropy oxide, so which is the type of multiple oxide, contains the metal, 5 or more metal cations. So at least 5 metal are formed. And then this is the high entropy oxide. So this one shows the very good efficiency in the OER, which is the commercially available iridium oxide shows the best efficiency, but it's comparable with a commercially available iridium oxide. So we also tried all different characterizations, and this one also published in the small. So another thing is let's see, as we know, so as we shine the laser and we can decompose the solvents. So what will happen? So using different plates, cobalt, iron, titanium, or levidium, so we shine the laser, so we can produce transition metal carbides, so which is really hard to synthesize in commercial way. We need to add lots of high power and high energy to produce these carbides, but we can easily generate these transition metal carbides. And here, like a cobalt case, now here also using the pulse laser ablation using technique, and then here's the Insu Raman. So for the case of cobalt carbide and cobalt oxyhydroxide is the key intermediate, and for the OER activities. So we also get some help from the diabetic calculations. And another thing is like zip structure, 67 polyhedrons. We're using this laser to generate the zip, and then we use pyrolysis to generate the nitrogen-doped carbon hydroxide. Also, using in the Raman, Institute Raman studies, show the overall water splitting applications later. And later, we wanted to use 2 laser system instead of 1. So we wanted to use IR laser, 1064 nanometer, and another one, UV laser, 3055 nanometer. So for the IR laser, we can convert carbon, sp3 carbon to sp2, and UV lasers is you can reduce surface oxidation of the containing just like functional groups, and so we can generate graphene oxide to reduce the graphene oxide. So it also shows in good activity in oxidation, oxygen evolution reactions. And here also in cobalt case, cobalt oxyhydroxides and cobalt oxide are reactive intermediates. And another thing is under review now, and the high entropy alloys onto the surface of the multi-walled carbon nanotube. And here, interestingly, we did it in the KOH alkaline solutions, but we got these H3O+, the hydronium ions, is coming through we can monitor this in the in situ Raman studies. So it's happening even in alkaline condition. The HCl is really active in these the HEAs using ruthenium, iridium, platinum, and gold HEA materials. So another thing is, so we use the later, first time we didn't know was why this activity is really high, but later further investigation with high resolution TEM, we found that, there was a single atoms plays a really important role in activity, this catalytic activity, because we didn't know before that because the resolution was not too high enough. But later we found that a single atom metal plays this really important role in catalytic activities. So we can do photo reduction with the first laser irradiation, and we can control the particle sizes and also enhancing the active size for the electrocatalytic activations. And we further studied STM, EDS images in GNU, the high resolution. Another thing is high entropy Prussian blue analogs, HEA, PBA. So we can generate this to the cubic structures, and then we apply to these OER studies and also nitrate reductions, NO2-RR studies. So the details will be given by the, Dr. Theotically. So he'll tell about more electrochemical works. And it shows really high activity using these the high entropy alloys. It is really easy. I mean, you can shine the laser, and then it forms the high entropy alloys. Otherwise, it is really difficult to generate these high entropy alloys or high entropy Prussian blue analogs. And this is also another thing, is using this the ruthenium copper. The ruthenium copper we can generate with a laser system. We can generate HCP, and then surface is ruthenium is onto the surface of copper, and then we applied this. We changing the ratio of ruthenium, and we found as ruthenium amount goes up, the efficiency of HCl and also formaldehyde oxidation reactions much better. So also, as I mentioned before, we can reduce energy to generate the hydrogen. So much we can save energy for generating hydrogen. So another thing is like a zinc hydrogen battery nowadays is very popular. Other things. So we use this iridium, the nitrogen doped, like a nitrogen doped carbon here, and we analyze all morphologies, analytical analysis, and you can see also here we can save 1.91 volts, so we can save energy to produce the hydrogen. And also we apply to these zinc hydrogen battery studies. It's very stable, and also we can further do hydrogen zinc hydrogen battery studies. And later on I think it's a little different in my slides. And this is another one. I didn't want it to explain this one, but we can go further. And later here, we shine the laser not in the solution. So we shine the laser to with the air. So we can generate black titanium, which is really hard to generate black titania, but we can easily generate with in the air conditions. So we can produce the black titania with reduction of platinum surfaces. And this is also published in JPCC. So since I'm running out of time, so we can go really fast. And this one also we're using the first laser system, and then later it's a microwave to produce the nickel ion LDH onto the surface of nickel the fibers for OER studies. And another thing was we wanted to use this coffee Prussian blue of analogs using the CO2 laser. CO2 laser puts lots of heat to the surface of the PBA, so we can generate cobalt iron oxide. And then later, after using the laser, the empty inside, so we use this one for the for example here we can generate this ammonia from the waste, and also in the meantime we can generate the electricity. It's both. While generating electricity, we can generate production for the fuel. So this is covered in Angevante. And other things. I think I need to go really fast since we're out of time. So since I'm from the spectroscopy, we have a multiple spectrometer. So we can use InShu, UV, and Raman and things. Thing is that you can see this here. It's a droplet is here floating on here. Why are we doing this? Because we don't need any walls. If we need walls, UV visible, we need to change the cuvettes and glasses and quartz, many things. It takes lots of time and also needs lots of samples. But here we can use InShu, UV visible, and InShu Raman and IR and other things at the same time. So we do these multi-spectroscopic techniques for measuring the mechanism studies. You can see this is the side views, droplets there, and also we can shine the laser. We can synthesize inside of droplets and photoreductions, and from the ions, it's metal ions to the metal nanoparticles, and then we can synthesize and then characterize at the same times. No interference with other things. And we apply this to the black phosphorus, and using the laser, we can explore the BP layers. We apply to these HR systems. It shows the better efficiency than the black phosphorus. I need to go really fast. So this is a summary of my lab research using the lights. Using all the lights, different kinds of materials, and we apply to the electrochemistry energy and environment and sensors. And if you're interested in, we publish in Light, it's a Nature journal, and Life Science Applications, and we have got in large citations. So that please refer to this review paper. So if you are interested in. And this is my lab in research production in this year. So we have electrocatalysis mostly interested in, and we also photocatalysis. We are focusing on sensors and spectroscopy. So if you are interested in electrocatalysis or photocatalysis and sensors and spectroscopy, you are welcome to contact me. And since I'm the editor of a light science application, I was asked to, just advertise the light science application, one of the Nature journals. You can please submit to the Light LSA. And another E-Light is I think I'm doing the associate editor. So please, if you have good data, you can submit to the eLight. So it's a good journal for the photonics and using lights and the electrochemical works too. And I have lots of international collaborators from India and United States and Australia, Japan, Thailand, and all other countries. I'm really thankful for the collaborators. And mostly I'd like to thank my lab members, postdoctoral fellows, on research, professors, PhD courses, and master courses, undergrads, and all people really work hard to produce the good outputs of the work in the lab. And not the least, and these are since this is the Indo-South Korea-Thailand, and we have lots of collaborators coming to my lab. This is this summer, we got, last summer, but this summer we had a collaborative research meetings. Presenting, and Ambulagam and me here, and all other Indian research professors, postdocs, and other Thai people. And thank you very much for your attention. Thank you.
CASA, you have commercialized your product, so you can be safely crowned as the returning star of sustainable innovation this year, because it's been a successful collaboration with CASA.
Okay, thank you very much.
Dr. Tirthagiri mentioned this morning that he lamented that fossil fueled energy sources are used and we have to identify other sources. So your cutting edge developments, they can be a replaceable source for renewable energy. So we appreciate the progress that you have done in your research work and identified, like again Dr. Vijay mentioned this morning that our country is looking for zero carbon emissions. So without leaving carbon imprints or footprints, the pulse laser technique, I'm sure, is the better replacement for fuel, other fuel, energy sources. So once again, we appreciate the research that you are doing and for sharing it with our countrymen as well. So now this session is open for any queries, any doubts that you have. I think, can you please pass a mic? Yes, sir. You can identify yourself and then ask the query.
Thank you. Professor Chai, this is Anandan.
Oh, okay.
Yeah. So, it's a nice presentation.
Thank you.
I have one question actually. You prepared using laser ablation method, phase center cubic and other cubic actually.
Sorry?
Using hexane and acetonitrile, you get two different morphologies, phase center cubic and other cubic morphology. What is the reason for such two different morphologies?
Morphology, controlling the morphologies.
Yeah.
Yes, it's a very good question. I mean, since we are using laser and to the surface of the plates, and then it produces plasma plume, so which is very high temperature, about we can say up to 6,000 Kelvin, and also high pressure, gigapascal. So at the high temperature, even though it's a room temperature, we're using the condensed high power laser to produce plasma plume. And when it cools down, cools depending on the solvents. So solvents sometimes decomposed and then to the surface of whether the material is a catalytic activity, and they can form the gravity carbon layers. So most likely they form the spherical structures. So other materials without catalytic activity, and they form like a metal ion itself and slowly cools down, and then they get aggregates, agglomerates, and then aggregates, and then they becoming to the sometimes rod structures, sometimes cubic structure, depending on these metal. The solvent sources using, and also different. We don't know exactly what's happening, but we know this from our experiences. So we can say that okay, we wanted to use nitrogen doped, and we can use urea on sulfur, thio, other things. So we can control the morphologies, but not exactly what is happening. But that's why we are doing this, the institute studies of, by just, measuring the plasma plume and sometimes, cavitation bubbles studies. So it's majorly depending on the solvents and then metal sources. Yeah.
Okay, thank you so much, Professor Che. So myself, Dr. Danish, Assistant Professor, Department of Chemical Engineering, Aligarh Muslim University. So my question is, pulse laser technology actually includes thermal burst on the material through which you are making nanoparticles. So are there any cases of micro cracks or phase change during the synthesis of nanoparticles?
Can you say that again? Thermal what?
Pulse laser technology includes thermal burst, like thermal effect on the...
Yeah, it depends. A thermal may mostly get the IR laser. So IR laser gets lots of, if you shine the IR laser, which is known to be, thermal, heating system.
Okay.
So like a carbon dioxide laser. In that case, you can produce lots of heat. But in other cases, like UV lasers or other UV laser systems, you can just produce such a high temperature, but it cools really fast. But CO2 lasers, we constantly heating it. So two different mechanisms of synthesizing techniques.
So is there any case of micro cracking during the synthesis of nanoparticles? Micro cracking.
Micro cracking?
Yeah.
Oh, micro cracking. Oh. I haven't thought about it, but we're using different sources of a microwave, but micro cracking. Maybe then if we have to use a very light, small, energies or to just cracking, or there's many different lasers available in like nanosecond lasers, femtosecond lasers, and picosecond lasers. For the femtosecond laser, they just use for the fabrication of the surface because it just fabricates. It doesn't deliver the heat to the surface, so they do fabrications. But nanosecond lasers, mostly as you mentioned, and it gives some heat. Depending on the laser that we use. So micro cracking means, as far as I understand, maybe using very less amount of laser power, not to generate the deconstruction of the metal systems.
Okay.
Yeah, but I haven't seen this micro cracking yet.
Okay.
That's a good idea. Yeah.
Thank you so much.
Thank you. Yeah.
I appreciate it was a nice delivery and you tried to cover so many fields, and I appreciate that your university or your department has published so many manuscripts in last 2 years, and that will be beneficial and that will be inspiring for all those who are present here. My question is that you have tried to use 4 solvents out of those 4 solvents, which one is the best? And the second question is...
first question, 4 different solvents.
You have used 4 different solvents, but you have not made a comparison of them. Which is the best solvent you find out of deionized water, hexane and so on? Similarly, you have used HEA. It consists of 5 metals and forms an alloy. So which 5 metals are the best?
Which 5 metals are best?
Ruthenium, palladium and so on. So these are my 2 questions.
Yeah, I mean, it's a really good question. And it depends on whether what kind of application we want. And for the HER, like a case, we mostly using platinum. And OER is iridium. And sometimes the as I showed before in a cobalt, which shows excellent efficiency of HER for the transition metal case. Noble metal we can easily generate. But we want reduce the amount of noble metal. So by reducing the noble metal, expensive noble metal, we can use the transition metal, which is cheap, but equivalent to the efficiency of the one we want for the HER on OER case. So for the most of the stability wise, cobalt is good and chromium is also good for the one. But mostly for the high entropy alloys, we wanted to use the cobalt case because it has a different spin state. Sometimes spin up, spin down, and it produces different when you see the inorganic chemistry, there's a different metal to ligand energy states. So that 2 different states, spin states, or people also say cobalt 2+, but sometimes they say cobalt 3+. So they can they have a more higher probability for the reaction of the HER case. So we usually use we choose different metals for the different specific applications. Okay, thank you very much. That's a very good question. Thank you very much. Yeah.
There is any other query? There is anybody have any query?
Thank you, sir and ma'am. It is our pleasure that we witness such an amazing session. Thank you once again. Now I request our chairperson, Professor Dr. Deepti Shastri ma'am, to felicitate our speaker for the day.
Sir, thank you so much. It was an honor to chair your session. Sir, can you please come on stage? We would like to give your certificate. And as you come up, here's wishing that your pulsed laser technology will literally power our future.
Thank you, sir. Sir, I now request you to felicitate our chairperson for the day, Professor Dr. Deepti Shastri ma'am. Thank you, ma'am. Thank you, sir. We now move on to the next keynote lecture. I now welcome Professor Dr. P. Gnanashekhar, sir, Director, IIE, VMRF BU Salem, to chair the session.
Warm good afternoon to all of you. It's my pleasure to be here on the second keynote session of iNEEBA. I've just been going through the inaugural session and the first session. the type of research which is being done in laser technology. I myself am a computer engineer. So what was going through my mind about lasers, one of my friends went to a beauty clinic. In the board it was mentioned, laser hair removal, 50% off. And then my friend went there and started arguing, what about the remaining 50%? So this is the knowledge most of us have on laser. The type of research which is going on elsewhere, it's tremendous. And now people have been using laser technology for warfare. The recent Gaza Strip has been witnessing laser fireworks. So it's right time iNEEBA is taking these type of initiatives to update our academics on these topics. Now this session, I'm happy to introduce Dr. Teethagiri Jayaraman, who has been with us from the first iNEEBA. He has been instrumental in the arrangement we have with both the universities. I'm happy to introduce him. He is currently a research professor and a brain pool fellow in the Department of Chemistry, Gyeongsang National University, South Korea. His current research is focused on the development of electrocatalysts for the production of energy-saving fuel and value-added chemicals. Professional involvements of Dr. Teethagiri, he is an editorial board member in Bioengineered, in Science of Advanced Material journals, and also Associate Professor of Chemical Papers Journal. Dr. Teethagiri has published 175 referred papers in high-impact international journals, edited 2 books for Elsevier and 1 book for RSC Publishers, 20 book chapters and 4 patents. He has delivered several invited keynote and plenary sessions, lectures at various international conferences across the globe and academic institutions. Dr. Teethagiri, the floor is yours.
Thank you, Professor. Thank you for your nice introduction. So, I'm Dr. Teethagiri Jayaraman, currently working as a research professor in Myung-Young Choi's research group in Gyeongsang National University. So, I will share some of my research experience on the title of Pulsed Laser Synthesized High Entropy Material for Clean Energy Production. So, I understand that we are running late, in a lunch time, so I try to finish in a short, maybe within 15 minutes. Yeah, so I'm excited to see you again. These are some pictures we taken in iNEEBA 2023 in the last year. And sorry, this laser is not working, so I cannot point out. And here, Professor Anbalagan has visited last month for a week to our lab and to initiate a collaborative work. So here I have shown some of Korean traditional food, especially like ramyeon or some kimchi jjigae like this. So next slide I can show you. So as Professor Myung-Young Choi explained about detail our university and the Jinju culture. So this is the Jinju port. It's a lantern festival or night view. All the nights that Jinju port will be glow like this. So this is one of the famous and festival, lantern festival. Every month in the October, this festival will conduct. Nearly 10 million people gather in the month of October to felicitate this, to watch this festival. And this is the Jinju character. And these are the food like Korean noodles that Professor Anbalagan was tasted. And of course, if you visit South Korea, you must try this food. You really like it. So these are the core facilities. So we mainly work on the laser synthesized material for various catalysis like photocatalysis and electrocatalysis. These are within our lab. So also Professor mentioned about XAS, that was in India we have only one in North India. I don't know whether a synchrotron facility, and Thailand we have one synchrotron. And in Korea, we have one synchrotron facility. So in addition to this, it is really hard that XAS, getting XAS. So recently, the people started working on the single atom catalysis. So for this, yeah. So single atom catalysis, that was the best characterization technique. So as mentioned, Professor very detailed about the laser technique. Our lab especially focused on the pulse laser technique to produce various nanomaterials. So we are using a pulse laser ablation in liquid medium and pulse laser irradiation in liquid medium. There was a pulse laser deposition or pulse laser air medium also. So we are also working on a pulse laser air medium, but I am not going to talk about it. And deposition we are not talking, because deposition it's mainly on the gas phase reactions, but here it's a liquid phase we are producing a nanomaterial. So what are the difference between the ablation and irradiation? Means the ablation, which is a top-down approach, bulk material to fragmentation, and whereas in irradiation we are using a bottom-up approach, like nanostructure, metal ions to the nanostructure. The main major difference is in ablation we are using a focused lens, whereas non-focused lens used in the irradiation. So let us go to our topic, electrocatalytic hydrogen production via water splitting. So hydrogen fuel, which is used as a energy in the transport system, like in the morning introduction section we were discussed about it, the needs of clean energy, fuels. So it also used as a fuel production, and the industry feedstock as a value-added chemical synthesis, like ammonia, which is the best fertilizer we are using in the agriculture field. So there are various techniques which we are adapted to synthesize for the hydrogen fuel, but electrochemical water splitting considered as a green hydrogen, green chemical productions. So we know water, which consists of H2 and O2, when electrochemically it split, when we split electrochemically, the oxygen it evolved in the anode side, and hydrogen produced at the cathode part. So these are the thermodynamical potential, like Professor Myung Choi and Dr. Vijay mentioned about the optical potential. 1.23 is the OER, of course. Like anodic and cathodic, when we add it is a cell device potential also. Water splitting is a 1.23 volt. And here I have summarized the optical reaction, HER, OER, and overall water splitting reaction. So the performance of any device, electrochemical device, is mainly based on the electrode material which we used in the anode and cathode part. So when we search for these electrode material, new material, we need to focus on the improve the activity of electrocatalysis and the stability. Any device which we required a long device, like cell phone batteries, we required higher stability and the selectivity, especially Professor was discussed even in the question in section. They were talking about the selectivity of pace and like morphologies. So I don't want to go in detail in order to reduce my time of talking. So in a research also, like we have to, any research we have to plan for the less cost, like operational cost should be lesser and the performance should be higher with higher lifetime, and to avoid the pollution. So we need a clean environment. So one of the major focus of this conference is a clean energy production and clean environment. So these actually application point of view, we discuss like water splitting is a clean energy hydrogen production. Of course the synthesis technique also green chemistry process, because we don't use any surfactant or capping agent to synthesize the nanomaterial or electrocatalysis. In absence of any surfactant capping agent, what happen means it enhance that active sites. So when we use the, like in conventional technique in hydrothermal or solothermal, in order to control the morphology and size, we are using a various chemicals like a surfactant or capping agent. When we use it, blocks the surfaces. So all the electrochemical reaction is a surface reaction between the electrode and the electrolyte. So it block the active sites. So in this case of laser technique, these kind of issues we can avoid. So there is no byproduct, because we are not using A, B, C. No, we are not adding like a chemical reaction. Rather, we have one direct metal, and we can directly ablate, irradiate in liquid medium. So here you can see one of the work what we are like in our lab, as the professor mentioned a lot of the technique, we also trying to develop the technique, not only on the material, we are trying to integrate the various technique or to measure the integrated in situ spectroscopy technique to measure the, identify the reaction, mechanism. So we generally what we are doing, the researcher, we focusing on only, okay, I have synthesized the material, I took a XRD, then we are going for application, okay, this much potential is coming, this is my best material, like this we are reporting. This is the usual things. But what we are doing is what happening at the reaction, in the electrode. During the reaction, we are monitoring in the various in situ spectroscopy technique, how the phase transition takes place, everything. This is the mechanism, of course we are validating with the DFT, but DFT is always like illusions, like we are, it will be like this or something, but we have to match with the DFT using the electrochemical various in situ technique. So in this work we have integrated the laser with the sonochemical process. So what will happen is both, like sound, sonochemistry is a sound wave which also split the solvent into radicals. So in the same way, when we pass the laser also, when the solvent get decomposed, for example water, it can split into hydrogen and hydroxyl radical. These hydrogen radical act as a reducing agent to reduce any metal salt in, metal ions to the metal nanoparticle. So here we are not using any chemical reducing agent, for example sodium borohydride, which we used for the reducing agent. So these kind of chemicals we can avoid using the laser technique. These are the major advantages. So this work was explained, I taken from the Professor Myung Choi's slide. So what happened, we were talking about the selectivity. When we not only the different material, when we change the ratio of the composition in alloy, we can produce a different selectivity. For example, in case of HER, OER and hydrogen oxidation reaction, in this work we have performed. So whether all the composition is applicable for the, effective to the HER, OER or hydrogen oxidation reaction means no. Because for example, in this case, the highest PT loading catalyst A1 PT8, that the green color is the highest HER activity and OER activity, hydrogen oxidation activity, but in case of OER it is not best catalyst. So like AU1 PT4 was the best. So why it is not effective to the OER activity? Because during the electrochemical reaction, this PT converted into PTO, that is in the surface reaction. So this PTO hinders the oxidation OER reaction. So this was monitored by the various instrumental technique, like in situ technique. This is the beauty of this work, and what we are focusing in our lab is to monitor the reaction mechanism rather the application, how much efficiency it produced like this. So this is the work which we are developing in our lab. So these are the one best example, in situ Raman technique, where we can, for example, in the laser technique, if you want to produce the metal carbide material, it is a gas solid phase high temperature reaction. So usually what we can do is that they take a metal precursor and they pass a methane gas at high temperature. This methane gas decompose and induce the carbon. This carbon attach with the metal. So this is the time taking process, and also it consumes a gas high temperature. But here in this laser technique, within 10 minutes we can produce a various metal carbide. Actually these are the not limited, we can extend to the, we can check for the other various metal carbide, and we check for the HER, OER, and we measured using the in situ Raman, we captured the reaction mechanism, how this H2 produced, H2 evolved, O2 evolved. So what happened during the electrode material? These are the reaction which we are performing. And in another work, we will move on the catalysis, not only on the technique development, but we need to focus on the catalysis also. So we have a vast explanation, experience on the metal nanoparticle, metal oxide, metal composite like this, but recent trend was changed. We need to change to enhance the activity. So we move towards the binary, ternary to 5 and above metals combination alloys. That was a high entropy alloy. So this high entropy alloy, it has a above 5 and above metal. So what happened? What is the advantage when compared to the bimetallic or trimetallic? Means it has a multiple element in a single phase. So as we seen the techniques, like for example here all noble metals, high entropy we have doped, we have deposited on the carbon nanotube. Whether all these metals can participate in the reaction, HER, OER or hydrogen oxidation means no. So what are the major things means here, like in the in situ Raman spectrum, PT and ruthenium is played a major role in the performance of HER. What happened in case of hydrogen oxidation means like PD is the active site, reactive species. How it convert, during the reaction, during the performance, for example, I can fabricate an electrode. If I perform, we get a LSV, like this kind of LSV, and we think like potential is decreased, my catalysis is for good. Instead of going this simple research, we are going to measure what happening exactly, how this adsorption process and desorption takes place. This is what we are focused in this research, and we are continuing also. So like here mostly we focused on the noble metals. Here like a mixture of like noble and non-noble transition metals, high entropy alloy, we produced in 10 minutes. So making high entropy alloy in a single phase is the big task, which also can produce in within 10 minutes without any reducing agent. So here what happened is we could observe the high entropy alloy and high entropy single atom. So we use like single atom. Recent trend is there. Researchers are working on the single atom catalysis. So multiple, above 5 means high entropy single atom catalysis. So these anchored with high entropy alloy on graphene oxide. So in this work we perform different electrolyte, how the catalysis react with the different electrolyte, and we optimized it, and the result was like it is as usual. Generally that alkaline medium is good for the OER and acidic medium is good for the HER because of the reactive pieces. H plus ion is highly available in the acidic condition. So in another work, what we are doing is not only focusing on the hydrogen fuel, we also focusing on the ammonia fuel production, or we can apply in the agriculture field as a urea synthesis or fertilizers. So here what we did is like initially we saw only noble metal, then mixture of noble and non-noble metal. Here only transition metal based high entropy alloy we have synthesized. So we prepared how the morphology changes. For example, we prepared the PB as a template. When we irradiate, it converted in, upon the calcination it converted into cubic shaped oxide. So generally oxide means it form like a sphere, but here we synthesized in a cube shape. Then this was converted into phase conversion transition. It takes a sphere shaped alloy, high entropy alloy without any impurities. So this one what we the application we went for the nitrate reduction reaction. So nitrate is the mostly toxic pollutant. So we have a waste to wealth concept, and of course the professor has mentioned like killing one bird, killing birds with one stone with three applications, three benefits. Like he has his own like fabricated a device of battery, nitrate zinc battery. In the case of battery, what will happen, the nitrate has been reduced, the removal concept, and when we convert this toxic nitrate into ammonia, it's a fuel production, the second application. The third one is the battery application, so it produces the electricity. So these are the main focus of our research. So I think due to the time limit, I don't want to extend longer, or I don't want to explain in detail. So finally, I would like to thank our professor and director Myong Choi and our lab colleagues for the support. So I want to take a few minutes on this slide. If you can see here, like most of the things, like in the past research professor in the category, so I took from the process slide here. So myself working as a research professor, and Sendil Veluchami and Rahul JS. Actually, these are all like first three are Tamil, and the second one is Goa. And Rahul, what happened last year when we came the conference iNEEBA, he has approached us and he keep on emailing. So he is from Goa. I think he is associated with Dr. Jaygandan. He is working in a physics department in Vinayaka mission. So he is friend. And JS is from like Kerala. And if you take a PhD courses, almost like Akash Prabhu, Sundar Akash Prabhu is Chennai, and other one is from Kazakhstan, Sagantai. Ramar Govindasamy like Erode, I think, and Muttusamy is Tirunelveli, and like I think it is repeating something. Yeah. Saranya Anbarasu actually she is from Kishnagiri. So she also met last iNEEBA. She approached the professor and he has offered a PhD courses, and Vaji Miren is a Tirunelveli, I think. Sorry, Dindukal. And Raju is from the Bangalore. So almost what I want to propose is, if you are really interested to explore research and you want to do abroad, you can send an email to professor, or of course you can send me, or you can search our lab website. There you can find a number of opportunities and about more detail about our lab work. You can send an email. The main thing is, of course, n number of applications we are receiving. Each day at least 2-3 postdoc application professor was receiving, but all things we cannot, is not offering. But we need to selectively, those who are really interested, you will get it. That's what I want to say. So if you are really dedicated, you can approach professor. You may have a good chance to do your PhD. Of course, the two, last year 2 of Indians were completed their PhD. One now is in Canada. Another one is one lady. She is from Mangaluru. She was in USA. I think currently she is working in USA. So I think thank you and all the best. Let's hope at least one person from this group will be in our lab member, if you are really interested. Yeah, thank you. And if you have any questions.
Thank you, Professor. I am really happy to note that iNEEBA has been a platform or gateway for people to get into research into GNU. It's wonderful to see more people coming in. We do hope someone from this group also would join your research group. We'll have the floor open for just 2 questions. I feel people are hungry, so we'll close. Yes, sir.
You talk about the Prussian blue. Yes. Prussian blue is generally cubic form. Yeah. How you convert a cubic form into spherical or something? That's I want to know.
Yes, Prof. So this cubic form, when we heat it, when we calcinate it, this converted into oxide. So all the nitrogen, it evolved, and carbon, CO2 or something, it will evaporate, and finally it forms as a oxide, high entropy oxide. This was the conversion of Prussian blue, high entropy Prussian blue into high entropy oxide via calcination. 350 degrees Celsius, when we heat treated anything, any substrate template, it converted into oxide in air media. That one upon when we irradiate with a laser, what will happen is in ethanol. So when we pass the laser into any solvent like ethanol, here we used this ethanol, decompose and produce the radical like hydrogen radical and methane, CH4 dot, like a radical, methane radical. This radical is act as a reducing agent, a conversion of oxide to alloy. So when it convert, it form as a spherical. using a laser. Yeah. Thank you, Bruce.
Thank you, Doctor. Thank you for your wonderful session.
Thank you. I think we can discuss it later in lunchtime also. I think we are running.
Yes, sir. Yeah. Thank you all. Thank you for the session.
It was a knowledge-filled session, sir. Thank you. Now I request our chairperson, Professor Dr. P. Gnanashekhar, sir, to felicitate our Professor Dr. J. Teethagiri, sir. Thank you, sir. Now I request Dr. J. Teethagiri, sir, to felicitate our chairperson, Professor Dr. P. Gnanashekhar, sir. Thank you, sirs. We'll have lunch break from now till 2:15. So I request all the delegates to kindly stick on to the timing. An important announcement. So post lunch there will be 3 parallel sessions happening. First session will be happening in Annapurna Auditorium here. The session of Dr. M.L. Aruna Kumari ma'am will be happening in Annapurna Auditorium here at 2:15. So the parallel session 2 will be happening in Data Science Lab, Computer Science Block, Engineering College. Dr. S. Anandan sir will be presenting there. Parallel session 3 will be happening in High Tech Lab 1, Administrative Block, and Dr. K. Shakti Pandi sir will be presenting there. All the oral presentation delegates, please assemble in that particular sessions at 2:15 sharp. I once again repeat, all the oral presentation students who have been allotted in that particular halls, please assemble at 2:15 sharp. Thank you. Lunch is being served in the AC auditorium in the nearby block. Thank you.